Hi everyone, welcome. Thanks for joining me. In this video, I'll be discussing the relationship between language and the brain. I'll discuss the concepts of contralateralization as well as important anatomical landmarks in the brain that are responsible for language. Let's get started. As you probably know, there are two sides of the brain, the right hemisphere and the left hemisphere, and different functions are largely relegated to one side of the brain or the other. The right hemisphere is more responsible for creative thinking, imagination, music, art, even emotional intelligence, while the left hemisphere of the brain is more responsible for analytical thinking, math, logic, and, as we'll see, language. Moreover, the relationship between the brain and the body is contralateral, which means that the right hemisphere of the brain controls the left side of the body, and the left hemisphere of the brain controls the right side of the body. The left and right hemispheres of the brain are connected by a bundle of nerve fibers called the corpus callosum, which allows the right and left hemispheres to communicate information with one another. Again, the parts of the brain that deal with language are located almost entirely in the left hemisphere for most people. So how do we know this? Well, there's a few pieces of evidence. First, researchers have conducted an experiment called a dichotic listening task. This requires the subject to sit with a set of earphones on, and in each ear, the subject hears a sound. It could be linguistic stimuli, such as the word dog, or non-linguistic stimuli, such as the sound of a dog barking. Results of this experiment reveal that linguistic stimuli are processed more quickly when introduced to the right ear. Why is this? Well, when, for example, the word dog is introduced to the right ear, it immediately goes to the left hemisphere of the brain because of contralateralization, where it is processed and understood. However, when the word dog is introduced to the left ear, that information goes first to the right hemisphere, but it must travel across the corpus callosum where it can then be processed and understood in the left hemisphere. This means that there is a right ear advantage for linguistic stimuli, but, interestingly, there is a left ear advantage for non-linguistic stimuli. A second piece of evidence supporting this idea that the parts of the brain dealing with language are located almost entirely in the left hemisphere, for most people, comes from patients who have had brain surgery. More specifically, some patients who suffered from epilepsy have had their corpus callosum severed, and this would reduce the severity of their seizures, but resulted in unexpected consequences in their use of language. So studies have revealed that these so-called split-brain patients were able to identify and name objects if they were placed in the right hand, but they were unable to do so if they were placed in the left hand. So why is this? Again, if an object is placed in the right hand of a split-brain patient, that information goes directly to the left hemisphere because of contralateralization, where it can be processed and named. However, if the object is placed in the left hand, that information goes directly to the right hemisphere. But because the corpus callosum has been severed, it cannot cross that bridge to the left hemisphere where it can be processed and named. The third piece of evidence supporting this idea that the parts of the brain dealing with language are located almost entirely in the left hemisphere, for most people, comes from patients who have sustained some sort of brain trauma. Studies have revealed that patients who sustain trauma to the left hemisphere of their brain are more likely to exhibit serious language impairment in the form of aphasia as compared to patients who sustain trauma to the right hemisphere of their brain. So what's going on in the left hemisphere? Can we identify important anatomical landmarks that are responsible for language use? As it turns out, we can. Here we have a profile view of the left hemisphere of the brain. Here's the angular gyrus, which transfers visual stimuli to Wernicke's area. Wernicke's area is responsible for language comprehension. Here's Broca's area, which is responsible for language production. And this is the arcuate fasciculus, a bundle of nerve fibers connecting Wernicke's area to Broca's area. So let's imagine that you're reading a word aloud. How does this process work in the brain? Well, first, the visual cortex collects the information as perceived by the eyes and passes it to the angular gyrus, which processes this information and transfers it to Wernicke's area, where it is then matched with an existing entry in the mind's lexicon and made available for recall. This information, a recognition of the word dog and its meaning, for example, then travels across the arcuate fasciculus to Broca's area, which takes it, and transmits the articulatory information, that is, how the word is pronounced, to the motor cortex, which directs the movements of the muscles in the vocal tract in order to actually say the word. Whew! This all takes place, of course, within a fraction of a second, and that's a true testament to the power of the human brain. These days we know a lot more about the brain than we did, say, a century ago, but there is still so much we need to learn. Who knows what secrets the brain will reveal in the coming years? Okay, that's all for now. Thank you so much for watching. I hope you found this video useful, and I hope to see you soon. Thanks so much. Take care.